So we're going to leap right in. Here's our statement of Green's theorem. Green's theorem says that if D is a region whose boundary of D, and this is terrible notation, and it's pretty standard that we use the same symbol for boundaries as we do for partial derivatives, but this is really just the outside part of D, boundary. Let's say that that boundary is a simple closed curve oriented clockwise. And we have these special restrictions that our vector field F has to have these two pieces P and Q to be continuous, and their partial derivatives have to be continuous. To be honest, these are things that I'm not going to test you on. These are sort of technicalities. And if F isn't a nice vector field, then this stuff isn't going to work out. But if F is a nice vector field, we get this crazy result. And by crazy, I mean cool. This is saying that the line integral along the boundary of D of our vector field is going to be exactly equal to the double integral over the region D of the partial derivative of Q with respect to X minus the partial derivative of P with respect to Y dA. What is this even saying? Let's draw a quick picture. So let's say that here's a picture of my region D. Maybe I'll do, D is going to be some region in green. Here's my D, it's a region. And then the boundary of D is this outside part. We're saying that the boundary of D has to be a simple closed curve, which means that it has to start and stop in the same spot. It can't intersect itself. We're calling this the boundary of D. Again, this is my notation. So this part is telling me, essentially, if I have some vector field F that's equal to PQ, I'm looking at the line integral, the vector line integral, along the boundary. I'll write that in words. This is the vector line integral along the boundary. And recall, one way to think of that is if F is some vector field that has all of these force vectors, that it's summing up the amount of work that I did to get around in a circle. You might think, oh, isn't that 0? And the answer is no, that my line integrals along closed curves are only equal to 0 if F happened to be a gradient vector field. So that was 16.3. Gradient vector fields, path integrals along closed curves are 0. But if F isn't a gradient vector field, then it actually could be some number, because it could mean that, like, if all of the arrows were pointing bigger on this side than on this side, that we could have some positive value for this vector line integral. So that's what the left side is talking about. What's the right side talking about? The right side is saying that instead of computing this line integral, if I felt like it, I could do a double integral over this area D over some new function. So this is a new function. It's not the function f, but it's a double integral, and I can break D up into a type 1 or a type 2 region, just like we did in the past. So I have some type 1 region of my x's and my y's, and I'm going to take the double integral over some crazy function, dA. Couple of comments. What is this crazy function, and why would this even make sense? Why would the integral of the outside be equal to some function, or the double integral of the inside over some derivative function? And really the roots of this, and we are going to go through a proof. The proof is really difficult. We know that with like regular integration, our fundamental theorem of calculus tells us that if we wanted to, we could evaluate an integral of f prime of t. I should have prepared this a little bit. So the fundamental theorem theorem of calculus tells us that I could look at as t goes from a to b of f prime of t dt, the antiderivative of the derivative function, this is going to be the same as f of b minus f of a. So notice that this area, instead of computing the whole area, we can compute it just at the endpoints. It is analogous to a certain degree, that instead of computing this area over the region, we're computing it not at the endpoints, but we're computing it along the boundary. And notice that instead of having a derivative function that's just the derivative on the inside, we have this crazy derivative function, sort of, meaning that we're taking some partial derivatives of some of the parts. So this is where I want to talk a little more about this particular part, because this part has a name. It's called the curl. So let's say that f is a vector field where the first component function is given by p and the second component function is given by q. If we look at the partial derivative of q with respect to x, notice that this is sort of backwards, that q is in the y component and we're taking the partial with respect to x. And p is in the x component and we're taking the partial derivative with respect to y. So these are sort of flip-flopped of their position. But if I look at the partial derivative with respect of q with respect to x and the partial derivative of p with respect to y, if I look at that difference, we call this difference the scalar curl of f. And typically we'll just call it the curl of f because context will tell us what this is. And this is exactly the thing that's embedded within our Green's theorem. That our Green's theorem is looking at the double integral over our region D of the scalar curl of f. What is the scalar curl of f? It actually has pretty cool geometric implications. That if I were to look at some vector field, maybe I should have drawn this vector field in advance, so bear with me. So let's say I have a vector field where it's always 0 in the y component, and it starts out small and gets bigger and bigger for our x components. And I want to know, what is the scalar curl of this vector field? What does it mean geometrically? And really what it's measuring is if I put a pinwheel down into this vector field, and I want to know, how would this pinwheel spin? Whoops. Asking how this pinwheel would spin is exactly asking what the scalar curl of f is. If my pinwheel spins in a clockwise direction, then our scalar curl is positive. If our pinwheel spins in a counterclockwise direction, then our scalar curl is positive. If our pinwheel spins in the opposite direction, then our scalar curl is negative. This is something known as the right-hand rule. So looking at this pinwheel, we would say that it has these tiny little pushes along the bottom because these vectors are little tiny vectors pushing, whereas it has these big vectors pushing along the top. And so our pinwheel is going to want to spin in this direction, right? It's going to want to spin in a clockwise direction. And so if our pinwheel is spinning in a clockwise direction, my right-hand rule tells me that I'm going to line up my right hand so that my fingers are spinning in the same direction as my pinwheel. And I see that in that case, my thumb is pointing in the direction of the scalar curl, and my thumb is pointing negatively. My thumb is pointing down into the board. So the right-hand rule tells us that with clockwise spinning, that's a technical term, we have negative scalar curl. Whereas if we have counterclockwise spinning, then we end up with positive scalar curl. That's because our hand would have been spinning in this direction, our right hand. Us left-handed people get confused sometimes because we start doing it with our left hand and have to say, no, This is a right-hand roll, not a left-hand roll. So I have to use my right hand to tell me the direction of the scalar per roll.